Okay, so this will be a little application of rate of change problems doing instantaneous rate of change and average rate of change. And I kind of wanted to introduce it with a little activity about throwing an object into the air. So basically what they're saying is the height can be found by using this equation here. Um, X is going to be the time in seconds, and then f of x will be the y value or the height there. So just to kind of get the ball rolling, I had you guys do a little sketch of the graph, finding the vertex, and then basically finding the zero. Okay, so a couple ways to do that. Of course, we could just throw into our calculator here the equation there, and then just a little peek at how I set my window up. This matches the grid that was given to you on your paper. We really only need to go from like 0 to 6 seconds, and the y's I went up to 200 with a scale of 50. And we can kind of see it looks like that. So we have a vertex somewhere up here where you could use the maximum command to find that. And then use the zero command on the calculator. So I'm not going to spend time doing that since we've done that before. But just so you can verify your numbers, this is GeoGebra. It just makes the graph look a little nicer. We can kind of see point A is going to be our maximum, so that's the vertex there, and then point B, when it hits the ground, was about 4.86 seconds, okay, which is point B down there just before 5 seconds. Okay, so let's get into some of the questions here. Let's find h of 1, and actually I meant to make this f of 1. I had changed it from h to f, and I forgot to change that part, but we had named the function f, so let's just keep it f. So f of 1 is really just going to be plugging 1 into the x's up here in this equation, and what it really is doing is just finding the actual height of the object at 1 second. Okay, so the easiest way to do that, using your calculator if you have the graph, you could either just pull the table up, or I like just going into trace and then just typing the x value that you want, and you'll get a y value of 161. Okay, so that would actually be the height there. Okay, so that height should be 161. And again, what that means is the height of the object at 1 second. Okay. All right, so now we want to find an average velocity of the object from 0 to 1 second. Okay, so basically if we think about the picture, okay, we know this point right here we just found was 1 comma 161. We could do something similar and find that the initial point is 0, and it started at 125, which I can tell was the c value there. So the average velocity is just going to be the slope of a secant line going through those 2 points. Okay, so average just means like a nice steady linear type of slope there. So all I'm going to do is basically use the second, I usually use the one on the right as this x2, y2, and the point on the left as x1, y1, and then I just do differences in the y values. Okay, 161 minus 125. That'll tell me how much we've changed in the y direction. And then just to show all the detail, it took 1 second to do that, 1 minus 0. So if we just do that subtraction there, and then we can get our answer, and that will be the average rate of change from 0 to 1 second. So in this case, it looks like 36. Okay, and again, that would be in what, feet per second, I think was our units here. Okay. So that one would just be, again, slope of the secant line turned out to be 36 feet per second. Okay. Moving on. Let's find an average velocity of the object. Okay, and that's what we're doing. The rate of change is velocity. If you think about the units again on this one, it was feet per second. Okay, change in y, change in x, so a slope or average rate of change is the same as the average velocity. So let's do this from 2.5 to 4 seconds. Okay, so again, if we know our graph is kind of doing something like this roughly, 2.5 seconds. Let me look at our picture a little bit. So from 2.5 to 4, right? So 2.5 seconds is about here to 4 seconds, which is here. And we're going to do the same thing we did in the previous part, where we're going to find the slope of that secant line. So something like that. Okay, and we just need coordinates then. Okay, so I would use the calculator in the table, in the trace, I mean, just to get those values. So if we go ahead and get y values, Okay, let's clear this out of here. So I'm just going to type, I'm still on that trace menu, so I'm just going to type 2.5, and notice it's going in as an x equals automatically. Okay, so the y value there is 155, and then for x equaling 4, we can get a y value of 77. Okay, and we'll do the same kind of thing. We'll get a slope of the secant line going through there. So it looks like 77 minus 155, and that would all be over 4 minus 2.5. Okay. Again, this is an average velocity. It's just the slope of that secant line there. So it looks like we're going to get up top doing the subtraction negative 78 and a 1.5 on the bottom. And when we do the division, it looks like around negative 52 feet per second. Okay, so that would be our velocity. And why is it negative? And I think we can tell looking from the graph basically. When we did the first part, from 0 to 1, that was maybe from here to here or something, and that secant line was positive. But in the part that we just did, it was kind of on the downside of the graph. So the slope is a negative number, and that's because the change in y happened to be negative, right? We were like losing height as time still went positive. So it was a negative number over a positive number. Okay, so now to the newer stuff. Here's this equation, this difference quotient with the limits. This is technically the definition of a derivative. So let's do some work on that. Okay, and we know our f of x that we originally graphed was, let me make sure we get this right, negative 16 x squared. Yeah, so negative 16x squared plus 52x plus 125. Okay, and what we want to do, I want you guys to come up with a new function, okay, that's going to take the form of this limit, okay, all this stuff, and it's going to be able to tell you the instantaneous rate of change at any point you want along there. Okay, and again, let's pretend like this is just an x instead of a t. Okay, I went from h's and t's, then went to f of x's. So the x unit is the time there. Okay, so what we need, okay, if you look up here, we're eventually going to need to know f of x plus h. So I would just encourage you guys, let's just see what that is right away. And really all that's going to happen from the original function is we're just going to take the original thing, but I'm going to put x plus h in for both x's. Okay, anywhere there's an x is now an x plus h. Okay, so that would be the f of x plus h. Okay, again, notice both of these things became x plus h's, and everything else was exactly the same. Okay, so now we know the two things that we need to know in the numerator there, right? Because we also need f of x. That was given to us originally, so we know both numerator pieces. So let's plug those in. It's going to be the limit as h approaches 0. Okay, because again, I want that horizontal distance between the 2 points to be as small as possible. Okay, because I want to be just at an instant point. I don't want 2 points like we did on the previous question. And let's color code here. So the f of x plus h part is what we just did in red there. So negative 16 x plus h squared plus 52 times x plus h plus 125. Okay, and then we are subtracting. This was the regular f of x that we need to do next. So let's minus that whole thing in parentheses. Okay, and the whole thing is always divided by h. Okay, h is like the change in x. Okay, so now it becomes a really kind of a messy algebra problem. Okay, so let's do it. So we're still doing the limit as h approaches 0. Okay, what I'm going to do first is actually just kind of distribute out, or FOIL if you will, the x plus h squared here. Okay, notice that's really just x squared plus 2xh plus h squared. Okay, so just check the foiling. If you need to do that slower, go ahead, but that's something we should be getting comfortable with. I'm going to just do that one step for now, and I'll do all the distributing and the other stuff in the next step here. Okay, so I'm going to run out of space. I feel negative 16x squared plus 52x plus 125. Okay, so let's write a little smaller on the next line. And again, it's all still over h. Okay, so let's do the limit as h goes to 0. We've got a couple things to distribute, right? That 16 can go to everything first, the negative 16, I mean. So negative 16x squared minus 32xh minus 16h squared. Okay, we can distribute the 52 to both of those, so plus 52x plus 52h plus 125, and then distribute this minus to everything as well. So that would be a plus 16x squared, a minus 52x, and a minus 125. Okay, again, all still over h. All right, now here's where things might start to get better for us. We've kind of been doing all this algebra, and here's why. Now a lot of things should hopefully cancel out. Okay, if we look here, there's a negative 16x squared that can cancel out with a positive 16x squared. What else? There's a negative 52x and a positive 52x. Those both cancel out. Okay, there's a plus 125 and there's a minus 125 that will cancel out. Okay, and that might be it for now. Okay, so let's kind of clean up what's left and see what we got. So we have the limit. Still haven't done anything with h being 0 yet, right? So we have negative 32xh minus 16h squared plus 52h all over h. And again, I still can't substitute in 0 for h. Okay, if I were to do the limit here, if I were to do this, it would still cause me to have a 0 in the denominator. So what we can do though is once we're at this step, I can now divide every term by h. Okay, because this term has an h, this term has h squareds, and this term has an h. So if we do that simplifying, so we still haven't done the limit yet, but I'm dividing h out, so negative 32x minus 16h plus 52. Okay, now we can plug in 0 for h. It's not going to be in the denominator. It's not going to give us anything undefined. So if I took this h as 0 and plugged it in for that h right there, it's basically going to make that middle term become 0. So we will just be left with negative 32x plus 52. Okay, and that is going to be the derivative of the original function. That's the instantaneous rate of change at any x. Okay, in calculus, you guys will call that f prime of x. Okay, we haven't talked about that yet, but that's kind of the symbol that you'll use. The original function was f of x, that little apostrophe, we read prime. Okay, so you'll see a little bit of that. What that allows us to do now, this will give us the slope of the tangent line anywhere. Okay, this equation is not giving us the height of the graph. That's what the original f of x was. Okay, to get the height somewhere, we're using this f of x that we started with up here. Okay, that's the height function. That's regular f of x. We now have the derivative of that, 32x plus 50, I'm sorry, negative 32x plus 52. That will give you the slope of the tangent line anywhere. Okay, so the next question was, what is the, or first we want to draw the tangent line at t equals 1, okay, and then use our answer from part E to find the slope. So at t equals 1, if we look at the graph, okay, so t equals 1 is about here, a tangent line there would just barely graze it like this. Okay, and it's hard to draw these, but I can see the graph is definitely increasing, so it would be a positive tangent line like that. And whatever the slope of that line is, that's going to be our instantaneous rate of change. And that's what we want to try and find. And that's what the equation that we just did in part E will do for us. Okay, so what I'm going to do is go ahead and plug in. They want us to do this at 1 second. Okay, so I know the function was negative 32x plus 52, right? So if I plug in x equals 1, that would give me negative 32 times 1 plus 52. Okay, and that to me looks like it should be 30, right? It's negative 32 plus 52. So 30 feet per second is going to be the instantaneous rate of change at 1 second. Okay, and the good thing about knowing this function here is you could do it for any time you wanted. If you wanted it at 3 seconds, 4 seconds, anything you want. Okay, you can just plug in the x and get that value. Okay. Okay, and again, that's the slope of that tangent line. Okay, so let's go back to average rate of change. Okay, from launch until we hit the ground, right? So when we launched, this thing was at, look at our graph here. Again, that point there is at 0, 125. And when we hit the ground, way down at point B here, it was like 4.86 seconds, and the y value, of course, when you hit the ground is 0. And all we need now is a slope of the secant line going through those 2 points. Okay, that'll be the average rate of change. So let's find that. Okay, so basically I'm going from 0, 125 to 4.86, 0. And the slope there would of course be 125 minus 0 over 0 minus 4.86. Okay, so it sounds like 125 over negative 4.86. And doing the division there gets me a slope of around negative 25.72 feet per second. Okay, and make sure we're okay with that being a negative number. Again, looking at the picture, the blue line, like we started out higher than we ended up. So we were actually losing height overall, even though at first we gained height until we got to A, but then overall we actually lost height. So a negative average rate of change. Okay, so the question now is saying the last question, what is the what's the time? Let's pull this up here. At what time does the object's instantaneous rate of change equal its average rate of change? So basically, the average rate of change we just found. That was, what was it, negative 20, forgot that number already. Negative 25.72 feet per second. Okay, so they're saying, is there a time when its instantaneous rate of change equals that same number? Okay, I know the instantaneous rate of change at any time is what we did in part E, I want to say, down here, and we did all the work. Okay, at negative 32x plus 52, that's the instantaneous rate of change. Okay, so our job is to figure out when will this thing equal this. Okay, so I'm just going to make an equation out of it. Negative 32x plus 52 equals negative 25.72. And see if we can find the x value that makes that work. So just a basic old equation. So we could start out by subtracting the 52 and divide by negative 32. And I'm getting around, so a couple steps in there, but again, just solve it like a normal equation. I'm around 2.43 seconds roughly. Okay. So just to visualize real quick what we just did is to finish this out. Again, the blue secant line there is the average rate of change of the whole thing, or the slope of that, I should say, is the average rate of change. And what we just said was at about a little less than 2.5 seconds, so somewhere right around here, kind of, the tangent line there would have the same slope as the blue line. okay? Because the instantaneous rate of change there is the slope of this tan line. And it seems about right. It seems parallel to the blue line roughly. I mean, I didn't draw it perfectly, but seems like it's in the ballpark there. Okay, so hopefully that helped. Make sure when doing these again, we're clear on the whole average rate or the instantaneous rate of change thing. Um, I'll just put up the quick little picture so we can visualize it if you're having trouble making sense of it. Better than memorizing it. If you really understand what's going on. The whole idea is this: if you have some function doing something like this or whatever, that there's some f of x, and let's say there's some point here that you're interested in. Okay, so the coordinates there would be x and f of x. To get the instantaneous rate of change, it's going to be the slope of a tangent line, okay, which would be roughly like that. And the way we're setting it up is by saying, imagine if there's another point out here, and I'm just going to make it a little far away just for the sake of being able to see it better. And instead of calling that x2, we're really saying there's some horizontal distance that we went away. So this is actually just x plus whatever that h value is. Okay, so that's the x coordinate. The y coordinate is the f of that. Okay, and what we're doing is saying we want to make that point as close as possible. I want this distance to be as small as possible. So what we're doing is actually limiting that h. So that's why it becomes the limit as h goes to 0. And the rest of it is just the slope equation. It's the second y minus the first y over the second x minus the first x. Okay, and of course the way we write it is that this and this cancel out, so it's really just an h in the bottom. And there's your definition of a derivative real briefly. Okay, so hopefully that helped, and that is that.